Welcome, everyone. This is ULM's Introductory Chemistry 1001. Glad you're here working on Chapter 8. Chapter 8 is very cool because it's useful in the medical field and industry, and we run on biological buffers. We're alive, thankfully, because these exist. So let's get to it. Buffer solutions, solutions which resist large changes in pH when either acid or bases are added. So if we have a buffer solution, it does exactly what buffer means. It means to weaken the effect of something so that something is less effective in causing a change. And that's good in many cases, like buffers against stress, right? Or buffers against going broke. All these things are important, but chemically, a buffer is some way to keep the pH from fluctuating wildly. We don't want pH changes from 7.4 all the way up to 9.4. We don't want pH changes of 7.4 all the way to 5.4 in the predominant bloodstream. That would be dangerous. So we have to be careful. And we luckily have enzymes and small molecules that help buffer acid and base additions to our system so they're not so effective at causing pH change, because we don't want pH change in this case. We want homeostasis. So these solutions we can prepare these in the lab too, as well as use it to control the pH of a chemical reaction and keep the chemical reaction at a certain particular pH that it reacts best at. So, but looking at the biological part, blood is a complex natural buffer solution. It has carbonic acid and bicarbonate ions predominantly in the bloodstream. It also has carbonic anhydrase and other enzymes that help to maintain this buffer. It's not just ran on small molecules, and it also has proteins or enzymes to help this be maintained as well. But we can set up even more simpler buffers where it's just a weak acid with its salt. And we'll look at what that means. You've already seen this. You've looked at weak acids, and you know that acetic acid forms acetate, right? So acetic acid or vinegar loses a proton and forms acetate anion. That is an acid with its conjugate base. And we're going to see why that's important. We also see the same thing down here we have carbonic acid, and then we have the conjugate base, which is the bicarbonate ion, and the bicarbonate anion can accept a proton, and the carbonic acid can donate a proton. So we'll look at that later on. But what this does is keep the pH of the bloodstream around 7.4. And so the buffer process, buffers act to establish an equilibrium between a conjugate acid base pair, okay? Or should I say an acid and a conjugate base. I don't really like that definition. I think they may have made, I don't know what they're doing. I didn't write all of these slides. I've made changes, but let me cross out an acid and a conjugate base. Let's call it C, because the result of an acid ionizing is its conjugate base. That may be right in a more broad context. We don't want to go skip what they said here. Let's look at this for what it is. A weak acid and its salt is the conjugate base. So if we have acetic acid, which is vinegar, that's the weak acid, and then we have the conjugate base, right? Okay. Water, I guess we could call water a weak base, and this a conjugate acid, okay? Because that is the pairs. We have the acetic acid with the acetate anion, and we have water, and then the resulting hydronium cation. So an equilibrium can be established in solution. We've looked at calculating, or we've looked at, should I say, with KW and things like that. We've looked at how to calculate acid and base previously pH values using the log of the concentration and then taking it to the negative, and then we get the actual pH value. So a buffer, however, is also based on Le Chatelier's principle, and we talked about that as well in our last chapter 8 discussion. So this is the buffer process. We need a weak acid and we need a conjugate base. And this I agree with this. A weak acid and it's salt, which is the conjugate base. So this is a weak acid, as we've learned, and this is its conjugate base. And we have water acting as a base because it's remember it's amphiprotic, and we can, as water can take on a proton, then the conjugate acid forms. So what happens to this buffer when we add base? What happens to this buffer when we add acid? Can we do both? Yes, that's the whole great thing about buffers. It can take additional strong acid, it can take additional strong base. Now, at some point, if you add too much acid or you add too much base, you will destroy the buffer, okay? But that depends on the concentration you have of your acetic acid and your salt. When I say salt, we have, let me switch to laser. Just for the terminology, that is the weak acid, and this is the conjugate salt. And so you can create buffers by adding equal amounts of acetic acid and equal amounts of the conjugate salt. That is artificially done. We have to create those buffers because in reality, the Ka, which is the same as the equilibrium constant, but for the acid, so we distinguish it as a equilibrium constant for an acid, which has to be a weak acid, by the way. Strong acids do not have equilibrium constants, right? Because they do not have a reactant and product, a product and reactant. There's only the reaction and it goes to completion and it's complete product at the end of the reaction. Not so with weak acids. We have an equilibrium constant with any reaction that doesn't go to completion, any reaction that will go from reactants to products, products to reactants, we're going to have an equilibrium constant. Since this is an acid, we can call this Ka, which is an equilibrium constant of an acid. And what we can do is we can set the concentration, the molarity, which is moles per liter of the acetic acid, equal to the moles per liter of some maybe sodium acetate. And this will work to give us a way to buffer both base addition and acid addition. So, but let's look at what happens when we add a base. Okay, let's say we add hydroxide. What will that do? Adding a basic substance to a buffer obviously causes changes. The hydroxide will react with the hydronium cation producing water. So what will happen here is OH will grab this proton here and it will end up forming water. And in that, that you lose this acid, you will end up you will end up with the buffer system will disassociate to replace the H3O. So let's draw an arrow. So we lose acid, we lose hydronium cation. If we lose hydronium cation because we added base, the equilibrium is going to shift this way to produce more of the acid and more of this conjugate base. So the net result is to maintain the pH close to the initial level. So you take out acid, it produces, you add base, it's going to produce, the buffer is going to produce a little bit more acid to keep it the same. So the loss of H3O, which is a stress, is compensated by the dissociation of the acid on the reactant side to produce more hydronium cation. And of course, more acetate as well. So if you take out H3O, you're going to shift the reaction to compensate for that. You're going to shift it to the right, to the product side. What happens if you add H3O? What happens then to the buffer? Well, if we add H3O, let's make it as simple as possible. Here is what we've added. We've added hydronium cation, so the concentration of hydronium cation goes up, And now the pH is gone up. And so what's going to happen is it's going to shift to make more of the reactants, which is water and the acetic acid. So the acetate anion and the hydronium cation, the proton will come off the hydronium cation, reassociate with the acetate anion, and shift to the reactant side of acetic acid and water. So this is how the stress is relieved. Okay, now this will make more of the reactant. So if you know Le Chatelier's principle, you know what will happen in a buffer solution. You will know what happens when you add more acid, you will shift to the reactants, and you know what will happen when you add more base, you will shift to the products, and you have enough concentration of this buffer you created. And how do you create a buffer? You create a buffer by having equal concentrations of CH3COH and the anion. So to a buffer, if we were to be as simple-minded as possible, which is good sometimes, we have CH3COOH, the buffer we create, we're going to have, and I'm going to put brackets around here to represent concentration, and then we're going to put equals the concentration of CH3COO minus, and then maybe we have sodium here, but sodium doesn't need to be included because it would be a spectator cation anyway, so we can ignore that. So the acetic acid equals the concentration of the acetate ion, and that would give us a start for any artificial buffer that we would create. Okay, so additions of acids or base to a buffer solution, these effects may be summarized as following, which when hydroxide is added, the equilibrium shifts to the right because what we do here, we have OH, and we will take this out. And then we will shift the reactants to products because we lost hydronium cation because it reacted to form water with hydroxide. So, but when H3O is added, if we add acid, we will shift to the left, or we'll shift to the reactants, right? So remember, this comes from Le Chatelier's principle. It makes sense. If you understand Le Chatelier's principle, then you can understand what a buffer does. And that's one of the whole reasons we taught you Le Chatelier's principle. And buffer capacity, what is that? It's the measure of the ability of a solution to resist large changes in pH when a strong acid or strong base is added. It describes the amount of strong acid or strong base that a buffer can neutralize without significantly changing the pH. Now, we're not going to give exact values in this class about buffer capacity. You're not going to have to do those calculations. You should know this definition about what buffer capacity is. You can exhaust a buffer by adding too much acid or too much base. Hopefully, you don't do that if you're doing a reaction in lab and you have calculated the concentration of the acid, the weak acid you need, and the conjugate base you need to create this buffer. And of course, these go into water solutions. And then we deal with hydroxide and hydronium cation, which we know can come from water. In pure water, it's actually present in very small amounts. Now, determining the buffer pH, buffering process is an equilibrium reaction. So we're back to KEQ or KC. So we can put the products, the concentrations of the products over the concentration of the reactants. In this case, for a buffer, it gets a lot more specific. We get the product in the numerator, which is the salt, or the anion, which is the acetate anion. In this case, we don't put sodium or anything else in here. We ignore it because it's a spectator anion. But then we put the acid form, the hydronium cation, the acid concentration, which will determine the pH of the solution, by the way. We could take the negative log of the concentration of hydronium cation, and we could get the pH, right? Negative log times the hydronium concentration would equal the pH. Okay, so now what happens remember I told you this trick, about making the acetate anion equal to the acetic acid concentration, making the concentrations equal. And when these are 1 and 1, they would simply cancel out. And that's not always the case, but if it is, then Ka simply equals the hydronium cation concentration, and therefore is the pH of the solution. And you can look up Kas, and you know if you add weak acetic acid and the acetate ion in equal concentrations, the Ka value can be used to determine the pH. So if you want to know the pH of the buffer, you can solve for the hydronium cation concentration and then calculate pH by negative log of the hydronium concentration. But if we were to rearrange this, because we could have more complicated problems when you take more chemistry, this class, I'm going to keep it simple. I just want you to kind of see what's happening. But the acetic acid concentration or the sodium acetate concentrations are both listed as 2.0 times 10 to the negative second molar. So we know that this is 2.0 times 10 to the negative second, and this is 2.0 times 10 to the negative second, and we don't know what this is. So we can solve for Ka and the expression for hydronium cation. Let me switch. So we can solve for Ka and therefore also the hydronium cation, which will be the same because these two are equal. It's not always like that, and you can't always do that, but in a buffer situation where you build the buffer from scratch in a laboratory, you can do this. So let's go ahead and we rearrange this, and we bring the acetic acid or the weak acid over here to multiply it by the Ka value equals to the hydronium cation and the acetate anion, everything that's in the numerator here. And then we can just divide both sides by acetic or the acetate anion, excuse me. And therefore we cancel out acetate over here. And now we have acetate in the denominator here. And so now we can solve for the hydronium cation. This gets easier because we know the concentration of both the weak acid and the acetate or the salt that we added. Okay. And so we calculate the pH of the buffer. We can assume, that the acetic acid represents the concentration of the acid component of the buffer, and assume that the conjugate base or the salt represents the concentration of the product from our equation. Remember, acetate shows up on the product side of this acetic acid equation. So the acid, the weak acid, is here at the top, and the conjugate base is here at the bottom when we rearrange this equation to solve for simply hydronium cation or the protons. And so if we put the numbers in, we can get pretty simple that the acid is 2.0 times 10 to the negative second. The conjugate base is 2.0 times 10 to the negative second because that's what we made it. We idealized it. And then we got Ka, which we look up or in a table or it's given to us. And then we know the hydronium cation is going to end up equaling the Ka value in this situation, which is good. It makes our life easy. And so now we negative log, we put in 1.75 times 10 to the negative fifth. We take the log of that. We're going to get a negative 4.76 times the negative, and we're going to get 4.76. So it is somewhat acidic, and if we need a buffer that stays around 4.7, 4.8, this is an ideal way to do it. We might have some reactions that need a slightly acidic or a somewhat acidic conditions. It needs to stay that way. This can be the buffer for which a reaction occurs in. And our bodies do unique things too, because parts of our body are very, very acidic. Even enzyme pockets can be very acidic because the environment is controlled, it's compartmentalized, and it can be very acidic or even basic in small pockets of our body and our tissues and our cells that we don't even, it doesn't interact with the bloodstream, which of course is 7.4, which is a lot of volume of a human being. So try to wrap your mind around that. If it doesn't make sense, come see me. This has been Dr. Pryor, Chemistry 1001. I will see you in class. Have a great day. Take care.